Today we're going to look at a more advanced floating point example. Make sure you've seen the cool floating point example first before you look at this one. But in this one we're going to consider the first root of a quadratic polynomial. And we're going to use 64-bit IEEE binary floating point representation. And we're going to look at the round-off error near that first root. So this was the quadratic polynomial that we looked at before. It just simply has three coefficients, and in the example I've established what those coefficients are. And we know from that example that there are two roots. There's a root at x1 equals 1/3, and there's a root at x2 equals 1. And today we're going to focus on that very first one. In the cool floating point example, we were looking at a simple floating point system, but now we're going to extend the view towards that IEEE 64-bit binary floating point. So double precision, or 64-bit IEEE, is made up of 64 bits. There's one sign bit, there's 11 bits for an exponent, and there's 52 bits for a mantissa. And when you sum that up, that's 64 bits. So that's a double precision for a floating point representation in binary. That the exponent is identified here as signed is a little bit misleading, as you will see in just a moment. What I did is I spiraled out from the book and looked for some other sources, and I found some supplemental information in Wikipedia, which is this pretty decent graphic, and it shows the lower order 52 bits as the mantissa or fraction. So that goes from bit 0 position up to bit 51. So that comprises 52 bits that forms the mantissa or fraction. And then the exponent starts at bit 52 and goes to bit 62. So that's 11 slots or 11 bits. And the very highest bit, bit 63, is the sign bit. Okay? And the way that Wikipedia showed this is you have a leading one that's hidden. The leading one is hidden binary bit. So this is a binary floating point that has a leading 1, and then it's followed by 52 bits, starting from 51 is the most significant, all the way to B0. B51 most significant, B0 least significant, so that follows this pattern right here, that location. So those bits go there. This is a binary float, that's why it's shown as base 2 right there. And then you have the exponent 2, because it's binary. There is a bias on the exponent, so the exponent comes in as, you can think of it actually as 11-bit unsigned, and it is going to be biased by 1023. So E, whatever this E is, minus 1023. And then the sign bit, or the sign bit being a 0 or 1, is used as an exponent on the -1 in order to establish whether it's a plus sign or a minus sign for the float. So that's kind of how, the lay of the land looks for 64-bit double precision. And remember that leading 1, but at the end of the day, you take that 64 bits and you can segregate it into three pieces. Of course, there's the sign being the high bit. There's the unsigned 52 bits that are the lower bits. That's the mantissa or fraction. And don't forget that you have that leading 1 that's hidden. There's an unsigned exponent E. This is listed as unsigned. Usually E goes from 1 to 2046. That's the normal range. It's 0, in a special case, it's 0 for signed or unsigned 0. And you need that, and you need that. You need that. So if all of the bits are 0, that corresponds with 0, because E is 0, and then the fraction or mantissa is 0, so that identifies as 0. If the fraction is non-zero when the exponent is 0, that's called a subnormal, And we're going to avoid these for now. If you're interested later, I can tell you more about it, but we're going to avoid the subnormals for now. The other special case is E is 2047, and that corresponds to plus or minus infinity, and or not a number, and we're going to avoid the not a numbers for now. So subnormals and not a number, we're going to avoid those for now. But generally, you have E between 1 and 2046. So E comes in as, you can think of it as unsigned. That's biased by this 1023. So let's say that E is let's say that E is 1023. So it's kind of right in the middle of that unsigned swath there. So E is, if E is 1023, then that's going to be 2 to the 0 once you bias it. On the other hand, if E is 1, then that's going to make this exponent minus 1022, so that's going to be a very small number. And then the last case, maybe for extreme, is E is 2046, so that's going to make this 1023, 2 to the 1023, so a very big number. So that's how the exponent works. But for the most part, you've got that the mantissa really setting the resolution for the number. Okay, I'd like to extend what I just presented to you and sort of unify it with the cool and simple example that I spoke of in a previous video. So in that spirit, I'm going to take the binary 64-bit double and I'm going to represent it by a mantissa M that is an unsigned 52-bit number, and I'm going to represent it also by E is the biased exponent, and I'm going to represent it by S, which is the sign, which is going to be 0, 1, that sets the sign of the number. And the way I've done it is I've taken the mantissa M and I'm going to divide it by 2 to the 52. So M is an unsigned 52-bit number. When I divide it by 2 to the 52, basically I'm getting a fraction. And that fraction basically goes from 0 to just underneath 1. And I'm going to add to that the hidden or understood leading 1. And that's going to give me a number that goes between 1 and very, very close to 2. So that number, that floating point binary number, effectively, is multiplied by 2 to an exponent, and the exponent is biased. We talked about E normally going from 1 to 2046, and with that bias, that's going to take that from minus 1022 all the way up to plus 1023. So that gives a nice range for our exponent. And then the S being 0 or 1 either makes this a plus 1 or a minus 1 effectively. This seems to be a rounding system. I'm going to put that aside for now and revisit that later, why I say that. But generally speaking, like I did before, if I say FL of x, that's the function that takes a real value x and quote-unquote floats it. And now I've given some examples. So here, and these are all positive, so S is 0 and the sign is going to be plus 1. But here I've got exactly 1 that I'm showing, and so it's going to have actually a 0 mantissa. The exponent is going to be 1023. So that's exactly 1. And what I thought I would do is kind of plop down here and think about, well, what if I did the very next number that is representable, and that's actually taking 1 plus this machine epsilon in this case. So my mantissa in that case ends up being 1. Mantissa is 1, and the exponent is still 1023. So that's what that looks like. And when I float it, look for the floating representation, I get that many zeros in front of the 2. And then I thought I would take an example that is a little bit more than 1 plus eps. And I picked mantissa of 4000. Quite frankly, I said, well, let me look at what a mantissa of 4000 would look like. And it ends up being associated with this floating point number. Very, very much bigger than 1 plus eps, but really not that much bigger than 1, quite frankly. So you kind of get a sense of what the resolution is. So for the machine epsilon, I'm going to say accept what MATLAB is showing you as 2 to the minus 52. We're going to accept this for now, and we're going to come back and hopefully one day resolve the rounding system versus this machine epsilon. But as I say, for now, let's accept that. Okay, what I just did is I like to show the mantissa in a hex format. The reason I like to show the mantissa in a hex format is because I know that it's 52 bits, and I know that there's 4 bits per nibble, so I'm going to get 13 nibbles or 13 digits possible on the mantissa. And had I presented the mantissa in an unsigned decimal format, it would be quite unwieldy to carry that many digits and really understand what they mean. So I'll show my mantissa as a hex. So floating point, we're still looking at the floating point operation where we take a real number x and we're going to quote unquote float it, and we're going to think about the relative error and how it is less than the machine precision or epsilon. So we're going to do the same thing that we did before. And then in terms of floating point addition and multiplication, it's going to be the same thing again, where x and y are floats, but their product or their sum may not be, and you've got to do the floating point operation. And again, the relative error for multiplication or addition, we're going to say that that's less than or equal to the machine epsilon. So just like we had for the simple, cool floating point examples, we're going to have a number of generic operations, just call them row 1, row 2, etc. And any one of them is going to be less than the machine epsilon. This is going to be a little bit of a repeat of what we did in the cool and simple example, but we're going to return back to our quadratic polynomial where we have the coefficients a0, a1, a2, and we're going to apply the Horner sequence. And when we do that, the Horner sequence basically is initialized with the highest coefficient, and then you take what you had before, you multiply by x, and you add the next lower coefficient. That's the first iteration of the Horner sequence. And you take what you had before that, and you multiply by x, and you add the next lower coefficient. And we only have 2 rounds of the Horner sequence for a quadratic. And it ends up being, remember, the 4 operations. We have a row 1 for the relative error for the first floating point product, a2x. We've got row 2 as a relative error for the floating point sum, a1 plus a2x. We've got row 3 as a relative error for the floating point product, which is a1 plus a2x quantity times x. And then we have row 4 as the relative error for the final floating point sum, where we just add in the a0. So remember, we're going to claim that a0, a1, a2 are floats, that we're looking at a proposed x being a float as a potential root. That's the point here. And when we do that, we're going to put together with the Horner sequence, we're going to say that that is equivalent to this is the first floating point operation where there's a notion of row 1 relative error. The second floating point operation is included with the notion of row 2 being the relative error. The third floating point operation is that product, and that's where row 3 comes in as the relative error. And then the final floating point operation is that last sum where you're adding in a0, and you're going to get row 4 for the relative error. So remember that that this side over here is achieved by way of the Horner sequence. And this is over here is a representation of the relative error. Okay, so I've just restated this, and what I'm trying to do is take what I had before and segregate it out to where I can get term by term. So I have an A0 term, I have an A1x term with its row factors. The A0 just had the row 4. And then I have the last term is the A2x squared, and of course it has all 4 operations present. Now, when I take the last one and I'm trying to simplify it and get the true value of the polynomial sort of pulled out of it, I end up with this. So in the approximation here, I've sort of set to 0 or assume to 0 any of the higher order terms like row 1, row 2. That would, since row 1 and row 2 are so small, their product would be very, very small. So you can assume that the higher order terms are set to 0, and then we would look at an approximation where I can pull out what would be the true value of the polynomial. And then for A0, I'm just going to pick up the row 4. For A1x, for that, after I expand all this, the only thing I have that's been non-zero or left as non-zero would be the row 2, row 3, row 4 linear terms, and then the highest order term A2x squared will see all 4, row 1, row 2, row 3, row 4 as linear. So now when I take the true value and bring it over with the floating point calculated value using the Horner sequence, I can say that the absolute value of their difference is going to be less than or equal to absolute value of A0, 3 times the absolute value of A1x, plus 4 times the absolute value of A2x squared. That all quantity times epsilon. So where this comes from, remember, is that, for example, you've got row 4. The absolute value of that is going to be less than epsilon. So when I take an absolute value of that term, I'm going to get that it is less than A0 times epsilon. And then when I do an absolute value of this term, I'm going to get that term, its absolute value is less than 3 times A1x times epsilon, because each of these rows are less than epsilon. And similarly, for the last term, I'm going to get the absolute value of that last term is less than or equal to 4 times A2x squared, because each of the rows here each is less than epsilon, so their sum must be less than 4 epsilon. So that's kind of how it was put together last time. Same thing here. So what from this is true for any x value, but what I really want to know is this x, is it a potential root? And so what that would mean is that the true value would actually vanish. If the true value could somehow vanish, then what would be left is just the floating point Horner sequence being less than the right-hand side here. And I'll call that, remember, I call that right-hand side error. And I sort of placed it so that, well, if I had a sign on the floating point, I could just say that the floating point Horner sequence is going to be greater than or equal to the error and less than or equal to plus the error. So that would mean it would be a root. So that's the calculated Horner. And this relation here is the error bound. I actually do it using a modified Horner because effectively it is a polynomial. The coefficients are like the original coefficients, but they're absolute valued. And there's a slight modification, a scalar, that goes with each term of the polynomial. So a slight modification. But when this statement is true, then x is a root within round-off error. So I showed you that for the simple, cool example. And now we want to go and look at it for the binary example. Here, what I thought I would do is walk you through a little bit of code, and it's similar to what we had before, but I've called it float 64b. So we're bringing in an x value, a real value that's coming in, real double, and we're going to split it up and show it as a structure. The structure is going to have a sign, an exponent, and a mantissa. I've got the x that comes in, I've really got to sort of typecast it. I've got to typecast it into an int64. So that's how I do it in MATLAB. So I have an integer typecasted representation of what that double looks like. And I need that in order to do the bit shift and bit mask operations. So after I do the typecasting to IX, I want to create some masks. I create a mantissa mask, and I'd like for you to check this out and figure it out. But I'm going to bit shift a 1 52 places to the left, and then I'm going to subtract 1. When I do that, I should get 13 digits of F. Okay, and that's exactly what I want for my mantissa mask. My sign mask is going to take 1 and it's going to shift it left 63 places. So that's, remember that the sign is all the way at the upper end of, the sign is all the way at the upper end of our float. And then I'm going to do an exponent mask, and for the exponent mask, check this out. I'm going to do an int64 of -1. So that is turning all 64 bits on, because a -1 is going to be all foxes, and it's going to be 64 or 16 nibbles wide, 64 bits, 16 nibbles wide. And then I'm going to AND that with a bitwise complement of an OR of the sign mask and the mantissa mask. Okay, so I'd like for you to kind of figure out what that means, and I'm going to turn debug on so you can actually see what the masks are, because I'm hexifying what those masks are, and I'm going to show you when I turn debug on. Okay, so that kind of gets us going. So we've got some masks. All we have to do is put those masks, do bitwise ANDs of those masks onto the IX, and we would have it. So the first one is bit AND of the sign mask with IX. If it's not equal to 0, that's what the tilde equal means. If it's not equal to 0, that means that that bit is set, and I'm going to set the structure xs.sign, that member, I'm going to set it to 1. Otherwise, I'm going to set it to 0. So the sign bit's taken care of. And then the exponent, let's do the mantissa next. So the mantissa is a bit AND of that IX with the mantissa mask. So that one's pretty easy. That one's easy. So that's my mantissa. And then what I do for the exponent is I do a bit AND of the integer representation of x with the exponent mask. I do a bit AND with the exponent mask, but I have to right shift it 52 places, because remember that the exponent is up here, so I need to bit shift it 52 to get the exponent over on that end. Okay, so that takes care of those 3 pieces, and then if I have debug on, I'm going to show, got this little show going here. Let's see what show does. Show is just going to print what the sign is. It's going to print the sign. It's going to print the exponent. It's going to print a hexified version of the mantissa, and then it's going to unravel it or unfloat it, unravel that structure to show what the floating point value is. And it's going to do it to 16 decimal places, which is the max. Let's see what else I got here. See what the float U does. Float 64BU. It does a similar thing that the float 2 or 3U did before. And basically I take the structure coming in, the mantissa, I do that hidden 1, plus I double the mantissa divided by 2 to the 52. And that takes care of that part. That takes care of this part. And then I take that and multiply it by 2 to the exponent structure member offset or biased by that 1023. So that takes care of that. And then I do the sign last, where I take -1 to a doubled version of x dot sign. So that takes care of my U or unravel. And then for maybe an add, it's pretty straightforward. I've got a 64B add. So I've got the AF and BF structures coming in. I unravel them, add them, and then I float them back and return it. So that's the add. Similar to what I did before, not a lot different. Yeah, I could do double representation, double floats, you know, sort of normal type things, but I thought I would show you this to be consistent with what I did before in the simple version. So here's the multiply. So you unravel, multiply, unravel both, multiply, and then float the result and send it back. Okay, let's do some examples. I'm going to turn debug on. And let's float 64B. Let's just do 1. Just the double, the real value of 1. What do we get? Okay. So it returns a sign of 0. That's true. The exponent is 1023. So that from a bias perspective, see if I can make that smaller. Yeah. So I've got a sign of 0, right, because it's positive 1. I've got an exponent of 1023, so that would be 2 to the 0, or 1 once you bias it. And then I've got a mantissa of 0, so that means I've got 0 divided by that. So really you just have that hidden 1, and that's right. Let's take a look at the masks here. I'm going to go back to this. Okay, so the mantissa mask, as I had promised you, I should have 13 Fs because I'm picking up the lower 52 bits, or 13 nibbles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I've got 13 Fs, so I'm picking up those last 52 bits. The sign mask is 8 with the rest 0, so that means that, yeah, this highest nibble here, this is 16 nibbles or 64 bits total. So the highest nibble is going to be a 1, 0, 0, 0. Yeah, that's it. So that's right. And then if you sort of look at the purpose of what I did, is I took the mantissa mask and the sign mask to create the exponent mask, and it really would be whatever remaining bits are left, that would be the exponent bit. So that's 7, you know, in the upper nibble. I'm going to have that bit on, that bit on, and that bit on, and that bit off, because I don't want the sign bit showing. So the 7 is good there, and then that's 3 of the bits, and then I'm going to pick up a 1, 2, 3, 4 more, and then a 1, 2, 3, 4 more. So you have that 7FF, and you see there's no collision, there's no collision between the exponent mask and the sign mask or the mantissa mask. And then when I printed or showed the result, yeah, I get 0 for the sign, exponent is that, mantissa, all zero bits, and then when I unravel it, I get a perfect 1. So that is float 64b of 1. Okay, so I thought I would do a float 64b of 1 plus eps. Okay, 1 plus eps. Let's see what that looks like. So 1 plus eps, the masks are going to be the same every time, quite frankly. The mantissa here is 1. I am 1 more than I was before. Before, with a perfect 1, I had all zeros for the mantissa. Here I have the next highest, and that would be just the 1 in the 1 position. And when I unravel it, that is where I'm picking up that the epsilon notification there, because remember, eps is going to be 2 and change times 10 to the 16th, so that's why that 2 is there. So that's 1 plus eps. You might remember that I did the example earlier where I floated the next higher representable number than 1, 1.0, a bunch of zeros, and then a 2 in that last location, and that was associated with a mantissa of 1. So we did that, and just to kind of complete the thought here, I might show this float 64b of, and I think I have this cut and paste ready to paste. Yeah, so I've got the 1 and then a bunch of zeros, and then I have an 8882 ready to go. Let's see what that gives me. Yeah, so the mantissa is 4000, and when I do the hex representation, I think I had FA0. Yes. Yep, so that looks good. Yeah, so it looks like I'm kind of ready to go to try to root this thing. Okay, I've written a script 64 here that is exactly similar to the versions I use in my Cool and Simple. I just changed the float 2 or float 3 to the corresponding float 64b's. So I've got my coefficients coming in, the same coefficients I had before. I literally just did a search and replace from float 3, and replaced it with a float 64b, this location. So I've got my coefficients structured up, and then what I'd like to do is look at that the representation, the floating point representation in 64-bit. What does that look like for the perfect root of 1 divided by 3? So I'm going to show that first, and then bear with me on this. What I'm trying to do is I'm trying to hover. I'm going to try to take the mantissa that I had from this 1/3, and I'm going to subtract 2000. So you kind of have a feel for what that subtraction of 2000 does to the mantissa. If you remember what I did with the mantissa 4000, and I'm kind of looking at a range of 4000, so I'm going to go the mantissa of 1/3. I'm going to subtract 2000 from that mantissa, and then I'm going to look at adding 1. So I'm establishing a range of floating point values that are around 1/3 plus or minus 2000 very fine floating point steps. Okay, so that's what it's going to do. It's going to take the mantissa and just increment every loop by 1, and then what I do is I unravel it here and then save it in my X, and then I take that structure and I go through those 4 floating point ops to implement the Horner sequence, and then I do the max error thing, same thing I did before with machine epsilon there. So I've got the machine epsilon dialed in right there. I also have this notion of factor. And what the factor is, a lot of times, since the EPS is so small, I want to know what factor of epsilon am I dealing with. So the stuff that would be in the parens here, I just repeat there, and that's just what I normally do is to keep track of what that factor is that multiplies epsilon. And then again, what I do is I take that last sum, and I kind of say the last sum would be the Horner calculated value of the polynomial that's associated with that x. And I unravel it and save it in a vector. And then my is it a root Boolean, again, is the z, and that's just looking at whether the floating point representation, what I guess would be the y, if that is between minus max error and plus max error. And then I do a very nice print, a little bit different than the print from the simple and cool example. I'm going to print x to 16 decimal places. I'm going to print a hexaphi of the mantissa. So I want to see what the mantissa is doing in a hex format. Then I'm printing just the signed version of the sum, the resulting Horner sequence. I just print the max error this time because I'm printing so many things in so many digits. So I print the max error to 16 digits. I print that factor to 3 digits, and then the last thing is a root. So I think I'm ready to run, and I don't plot here because everything is so very close to 1/3. There's just not a lot of range to even plot. But anyway, so let's see what we get. Spread this out a little bit. I think I can just say script 64, see what happens. Okay, so it's running 4,000 times, and you kind of see where the x ends up here, a little bit more than 1/3, and that's not a root. Let's go back to the top, scroll back to the top. Okay, so remember at the beginning, sort of printing out what that perfect 1/3 root would be from our structure perspective, and the exponent is 1021. So that means once you bias it, it would be 2 to the minus 2. The mantissa is 1. Remember the hidden one, and then you've got 3 zeros separating the rest of the 5s. So that's what the mantissa looks like. And now it says, hey, let's start the bit fiddling. So when you take that mantissa, you're going to have those 5s, but you're going to remember we subtracted 2,000 to give us sort of a starting point. So we're starting less than the perfect 1/3, 2,000 mantissa positions previous to 1/3. So that's where we're starting, and that's our polynomial calculated. It's close to 0, but it's not 0, and it is a positive value. We have a max error on the calculation, based on that modified Horner sequence. So that's our max error. And if I take that and think about what factor would multiply epsilon, it would be 6.33. That's what gave that error there. So that's where that factor comes in. And we're starting, it's not a root. So that's where we're starting. And then if you notice, the mantissa is incrementing by 1. So I went 4D86, 4D87, 4D88. So I am going max resolution. This is as fine as you can go from this starting location each step. So I'm not a root, and I'm not missing a root here. And all of the floating point Horner resulting values are still pretty big compared to what the error is. So let's start scrolling and seeing what happens. So as you can see, the x value is going towards 1/3, and our mantissa continues to just add that 1 like we programmed. Our floating point value of the Horner sequence is decreasing. It's still plus, it's still plus, it's still decreasing, but still grossly more than the error. So let me just kind of go a little bit quicker here. So we're making good progress. Our floating point value of the Horner continues to drop while our X is getting closer to 1/3 perfect. And let's see what happens. Still no error, no roots, no root. None of these are roots. We're still way above the 14. It seems like the error is kind of steady at 14 in those last 2 decimal places there. I'd like for you to figure out why that sort of looks static. And here we go. We're just kind of getting closer and closer to that 0. We're coming at it from the plus side. We're still just a little bit less than 1/3 here. Going on down. Okay, we're getting there. Still not a root, still not a root. Oh, look, we've got a root. So this floating point representation to within floating point error, this value with the 27 at the end, that starts the is root. So there's going to be sort of a range of acceptable floating point values that would, to within floating point round off, would be valid roots. So it starts there. Okay, so I've got 13 for my polynomial Horner sequence calculation. It's less than the max round off, and it's still plus, so I could still continue to sort of fine tune it. And you know what? I get down to what is exactly 1/3. Exactly 1/3 is, remember, is all 5s on the mantissa, so that's exactly 1/3. And you know what? It does actually calculate out to 0, and yeah, still root obviously. But if you notice, I actually get all 0 as well when I add even 1 more to the mantissa, but I'm still in a range that is considered a root to within round off error. We kind of expect that to be the one answer, but you know what? We can't distinguish that from that at all, because our floating point Horner result is still 0. And we end our range of acceptable values right here. Okay, so I think that's pretty cool. And then what happens is the Horner calculated value starts to become really negative, and we're no longer a root because we're too far negative. Its absolute value being much greater than the error. And you see the mantissa continue to add until we get to the end. So we're still quite a bit to go to get to the end. So we have bracketed that root quite nicely. So in our quest to investigate the area around this 1/3 root, we found a much tighter range of acceptable floating point values that are potential roots, much tighter, so tight we can't really plot it like we did for the simple and cool examples. And if we were to actually polish, the root, we could polish, and we would have 2 acceptable roots in this case. The one that is with the all 5s here in this location, and then all 5s and then a 6, 1 bit more. Those actually both each produce the all 0 for the Horner sequence. So those would be polished representations that we could report as the most perfect answers This is the floating point representation of 1/3. It's approximately 1/3. And dadgummit, I said earlier that the one with the all fives is, I said earlier that was exactly 1/3. And of course, it's the floating point representation of 1/3. So to within floating point accuracy, it is 1/3. And then, of course, the next bit. So a true 1/3 would potentially be between the two, and maybe that's why they're both acceptable. So in summary, the binary IEEE 64-bit floating point behavior, in other words, there's the range of acceptable roots, it's the same as what we saw in the cool floating point example, but with the accuracy or the resolution being so high, the range is much tighter of acceptable roots. And then we actually found two quote-unquote perfect answers such that the Horner floating point polynomial value actually vanished and was found to be exactly 0, and for the roots associated with that very close to 1/3, just the floating point representations of that. Note that this normally doesn't happen. You don't always find a situation where your function actually completely vanishes, and you have to sort of navigate that from a floating point round-off perspective, and you have to take the best route you can. So anyway, so I hope you enjoyed that presentation.